All right, today we're going to be atmospheric detectives. We're digging into the invisible particles floating all around us. The ones that have a surprisingly huge impact on our climate. Okay, let's get right into it. So, take a look outside. On a clear day, the air looks, well, empty, doesn't it? But it's not. Not even close. It is absolutely filled with microscopic stowaways, these tiny little particles that are secretly messing with the Earth's energy balance. The real question is, can we figure out who they are and where they're coming from? So our investigation kicks off with the main suspects. Now, the fancy science name for them is light-absorbing carbonaceous aerosols. But really, you can just think of them as tiny, dark particles that soak up sunlight and heat up the atmosphere. Let's break down our two prime suspects, shall we? First, you've got black carbon. Just think of this as the soot. It's the stuff that comes from burning fossil fuels, like the exhaust from cars and trucks. It is a really powerful warming agent. And then there's brown carbon. We can call this one the smoke. This stuff comes from burning organic things, like wood in a fireplace or farmers burning off old crops. It also adds to warming, just in a slightly different way. And here is why this is so critical. Scientists know for a fact these particles are warming the planet, but they are one of the biggest question marks in all of our climate projections. Not knowing exactly where they're from or how they act makes it incredibly difficult to predict the future of our climate with any real accuracy. So the huge challenge for scientists is that these particles don't just show up one at a time. Nope. In the real world, they're all mixed together in this complex atmospheric soup. And here you can really see the problem. It's like a police lineup of suspects from all over the planet. You've got soot from city traffic, smoke from wildfires thousands of miles away, dust that's blown all the way from the Sahara Desert, and yeah, even smoke from your neighbor's cozy winter fire. They all end up in the exact same air we're all breathing. And that's the central mystery, isn't it? For years, it's been like trying to pick out one person's voice in a massive, roaring crowd. How on earth can you pinpoint the source when everything is just jumbled together like that? Well, a new breakthrough is completely changing the game. Think of it as a new kind of atmospheric forensics, a way to finally get a clear, undeniable fingerprint from each and every one of our suspects. The whole idea hinges on this concept of an absorption fingerprint. See, it turns out that not all dark particles are created equal. Each type, whether it's soot, smoke, or dust, it absorbs different colors or wavelengths of light in its own special way. And that pattern of absorption gives it a signature that's as distinct as a human fingerprint. So how does this actually work? Let's walk through it. First, scientists zap an air sample with a wide spectrum of light. Then they measure how strongly the particles absorb different colors. They get one value for how much it absorbs the shorter, bluish light, and another for how much it absorbs the longer, reddish light. Finally, and this is the cool part, they plot those two values against each other on a 2D map, and that's what starts to reveal the aerosol's true identity. And this is where the magic happens. When you plot those values, different types of aerosols all cluster in different spots on the map. You'll see mineral dust over in one corner, fresh smoke in another, and traffic soot somewhere else entirely. It basically separates all the suspects for you, creating this amazing visual chart of exactly what kind of pollution you're looking at. Okay, so this all sounds great in a lab, but does it actually work out in the real world? Oh yeah. Let's look at some real-world case files from monitoring stations across Europe where this technique has been put to the ultimate test. Our first case file involves a massive, long-distance traveler. Dust from the Sahara Desert that pretty frequently makes its way all the way across Europe. So this fingerprinting method revealed something totally fascinating. It turns out mineral dust particles are really good at absorbing those short blue wavelengths of light, but they're not so hot at absorbing the longer red ones. This gives them a super unique fingerprint that just pops right out on that 2D map. Boom, case closed. We can now spot Saharan dust events easy. All right, next up, a completely different kind of culprit. Let's head to Italy's Po Valley, a place where agricultural crop burning is common and produces a whole lot of brown carbon smoke. The fingerprint for this fresh smoke, completely different. Its key trait is a ridiculously powerful absorption of ultraviolet light, which is an even shorter wavelength than blue. This UV spike is a dead giveaway. It tells you immediately you're looking at fresh brown carbon. It is a signature no other particle really has. For our last case file, we're heading into this city.
And here, the technique is so precise, it can actually tell the difference between pollution from a morning commute and the smoke from a winter evening.
I mean, just look at this data. The fresh soot from morning traffic has a pretty balanced fingerprint, right? But the wood smoke from winter heating, that has a much stronger signature up in the blue and UV range, making it look a little more like that brown carbon we just saw. And what's truly amazing is that as the soot ages in the atmosphere, it gets coated with other gunk, which changes its fingerprint again. We can literally watch pollution evolve in near real time. It's incredible.
So, we can identify the culprits, we can track them down, we can even watch them change. But why does solving this atmospheric mystery matter so much?
Well, it's a complete game changer. For the very first time, we can pinpoint pollution sources with incredible speed and accuracy. This means we can feed much, much better data into our climate models, getting rid of one of our biggest blind spots. That means policymakers can create smarter, more targeted rules to actually improve air quality. And on a basic level, it just makes all our black carbon measurements more accurate, giving us a way clearer picture of our impact on the planet.
This technology gives us a level of clarity we have never had before. The evidence is no longer invisible. And that leaves us with a really powerful final thought. Now that we have the fingerprints, now that we can identify the culprits with confidence, the real question is, what are we going to do with all that evidence? Thanks for joining me.